Okay, folks, time for the next talk. It's Sam Voigtländer, aka Userland Kernel, talking about researching iPhone Baseband. I'm very excited to hear this talk. I think the whole idea of mobile hardware security research is one that, the problems that it causes or the vulnerabilities cause are well understood, but how you get into actually understanding where things are broken and how they can be fixed probably isn't. So looking forward to Sam illuminating us all on that topic right now. I'll hand it over to you. Thanks, Sam.
Okay, thank you. Right, so I'll be talking about researching the iPhone baseband. It's a complicated subject. I want to state at first because the baseband is totally black box at this time. So I'll be explaining one another during the talk. Who am I? I'm some point 90 years old, still learning to code and security, but I've been doing this since I was 13. I'm now studying software engineering and cybersecurity, and well, my main interest is in mobile and embedded devices. So in my spare time, I also do non-profit research on these devices. So the reason why I decided to research baseband is because it's a thing that's not very much researched yet by a large scale of people, and this is because it's such a black box thing. Companies do not publish much code.
Hey Sam, this is Jason from the Bug Crowd team. You're coming through really in and out, and the volume's super low. Can you check your mic settings real quick? Make sure you're coming in through the right mic.
Sure. I'll put my mic a little bit higher. I'm sorry for the inconvenience. Can you hear me better now? Okay, so I'll just continue from here. So the reason why I started to research baseband is because it's totally black box and companies do not have a lot of details public about them, such as code, such as documentation about how they communicate and how they internally operate. So that's why I started researching it. And the baseband is a completely separated system. This system also means that the user has no control about it, and no control also means that you cannot verify the integrity and security of the device, which is makes it a very huge attack factor with a lot of problems to all companies concerned. Imagine your company being under attack by the devices that your own employees bring. So it's also radio communication, which makes it a huge attack factor as well, because they one corrupted baseband can work its way to corrupting other basebands as well. The likelihood of vulnerabilities existing in baseband is high. And this is because it's black box, no code is public, so not many people can discover vulnerabilities only with expertise, knowledge about the baseband. So my talk is also to make it easier for researchers in the future to examine baseband. My eventual goal was creating custom firmware for baseband chips so that SS7 attacks can be prevented with a firewall. Unfortunately, this was too complicated because it requires to know everything about the hardware of the baseband. But I've been able to research a lot and discover a lot. What is baseband? It's a chip on your mobile device. In my case, I researched the baseband used in iPhones. It's completely separated in iPhones from the rest of the hardware and the rest of the operating system. So it runs its own operating system, it uses its own secure read-only memory, its own random access memory, flash chip, and its own processor. I'll talk a bit more about the processor later in this talk. So what the baseband is mainly used for is cellular communication. So when you make a call, when you text a friend or a colleague, when you access the internet over LTE, that is all done by the baseband chip. And the only way the baseband chip is managed on the mobile operating system is through kernel drivers and a daemon basically interacting on the high-speed USB interfaces of this baseband device. And it also is a modem, so you can send carrier commands to the modem that the baseband understands. So the baseband in 32-bit mobile Apple devices is a Qualcomm chip in most cases. All the devices used Intel chips, but everything after the iPhone 3G pretty much uses a Qualcomm chip. One thing that was very special about such early chips from Qualcomm was that they supported voice over IP LTE calls. And the architecture is mostly 32-bit, but the newer iPhone 5 from the 32-bit Apple devices uses the Hexagon DSP processor, which is from Qualcomm itself. They developed this processor, and this processor also has some increased security mechanisms to prevent execution of certain memory. Communications for the baseband on iOS, Apple's operating system, go through the daemon com center and through the kernel extension. For the rest, there is no references to the baseband or whatsoever. So to learn more about this baseband chip in Apple devices, I started to look at Apple firmware. In the Apple firmware, IPSW, which is the format used by Apple, and is basically just a zip file that you can download through iTunes. There was another zip file called BBFW, which is the baseband firmware, and in that baseband firmware, another zip file, as I said, you can find binary images with an info property list file, an XML file containing information about the images, like the bundle ID, which is just a reverse DNS string, and some version information, probably because Apple needs to know a little bit about what firmware version it has on device. So the binary images are 32-bit ELF binaries, and that's pretty convenient when taking a look, because the ELF format has a header containing a lot about the references and symbols used in the binary. Sadly, the symbol tables and the symbol segments were left out, but a lot of information about the size of the segments and the code still was in there. What I also found through binwalk. Binwalk is a Python utility that you can use to examine firmware when you do not know what firmware it actually is. You can use it on any file, and it will tell you the offset of certain file types in a file, so that you can learn a bit more about the file. You can also look at the entropy for finding a lot about the structure of the file. And I used it, and I found that most baseband images also had a certificate at the end. So that means that they were code signed with a ticket, and certificates using SHA-256 signatures. In the main baseband image that you cannot see in the picture here in the presentation, but in another, I will show you it again. You can see the AMSS baseband image, which is the operating system of the baseband, and it's built upon the OKL4 kernel, which is a hypervisor kernel. I'll talk about that more later. So that operating system, the OKL4 kernel, is just a custom proprietary variant of the original OKL4 kernel, and they also seem to implement some Linux kernel, but you cannot see that, as that is in the protected random access protected memory, internal memory. So what I found from taking a look at this operating system is that there are shared memory devices over buses, in this case high-speed USB, that you can access, except they are all in their own context, as you can see here in the image on the right bottom. You can see that the OKL4 kernel's task, as it is a hyperversor, is to divide all drivers in different contexts and all apps in different contexts so that they are completely separated from each other for security reasons. Now, I'll show you a bit how this kernel looks like in IDA, because IDA was pretty much able to get a lot of functions back from the kernel. One sec. Yeah. So when looking at this, you can immediately see that this is an ARM image. These are ARM instructions. You have references to everywhere, but let's take a start at the header. At the header point, you see that it tries to load some data. Then you go a little bit below and you see that it does some memory initialization. I haven't had the time to. I had a file where I had the symbols and everything, but I lost it sadly. Anyway, as you can see, here is the first reference that tells you that this is the OKL4 kernel, and this is the heap initialization. And then this is very important. When an error is detected, this baseband device will enter download mode, which is a special mode, a protocol from Qualcomm for restoring whenever something goes wrong on the baseband. So you can flash restore images and emergency images. I'll talk about that later. And so looking further, there are a lot of more references to functionality, even metrics. So let's go to the strengths, because this might look a bit of complicated to you, but if I go to metrics, it will become clear to you that they also keep some metrics on device, and here are all the kind of metrics that they keep, which is surprisingly a lot of metrics. Validation, that kind of information. So this is something to look into because it's a very custom kernel of the OKL4 kernel custom version. So I also discovered that crashes will jump to environment RAM instead of the file system, which makes it a lot harder to fuss, because the crash logs you won't be able to see. You won't be able to see what registers contain values, so you won't be able to identify and debug crashes when they occur. And they did this probably because they do not want their firmware to be analyzed and their architecture to be broken in a malicious way. So let's talk a bit about the boot stages of the baseband chip. At first, you have the boot ROM, and the boot ROM, as you know, can only be flashed once, so you cannot change anything in here. And the boot ROM contains the root certificate, authority hash, and also the root certificate, authority certificate used for code signing. So that is where code signing will compare against. And you also have this bootloader on the boot ROM, which is called the primary bootloader. So the primary bootloader loads the bootloader from internal memory, and that bootloader has a signature, and that loads a custom kernel, so like the OKL4 kernel with the Linux kernel. But the Linux kernel runs outside the trusted memory. And it also has a signature. Everything is code signed. So how does this look? You have an ELF binary with a header, executable code segment, the signature of this code, the root certificate, then there's a special attestation certificate and some padding. So this header also contains a reference to the signature, the destination where the code should go into the memory of the baseband, the size of the image, and the actual code. So when taking a look at the actual ELF header, we learn that there are some other references, and well, in many times of bootloader vulnerabilities, one single mistake in parsing this header or having a wrong reference or having control over a reference without it being under code signing checks can bypass the secure boot. So that's why I display this header here. There are a lot of offsets, but Qualcomm states that they are actually validated. I'll talk about it later. There's the hash table segment, which also contains the code signatures. So about the hash table segment. You have the hash table segment with signatures of each part of the binary and a certificate chain. The certificate chain is basically 3 certificates: the root certificate, the CA certificate, and the attestation certificate. And each certificate verifies the signature of the next certificate in the chain. So you have the root key hash that's in the boot ROM. The root key hash validates the root certificate. That root certificate verifies the signature of the CA certificate, etc., etc. And this is how the secure boot mechanism kind of works. So how does Qualcomm parse their baseband firmware when it's loaded? Well, from their own documentation, I was able to get the following. An image is loaded into internal memory, and that internal memory is protected and trusted, but only available when the device is on. Makes sense, right? But external flash memory and random access memory are not trusted. Thus, an image must be authenticated within the trust boundary in internal memory. Now, I'll talk about that a little bit more, because there's a thing that sounds a lot secure, but it is actually not that secure. And of course, the ELF headers and the ELF program headers are parsed and validated. Now, eventually, the hashes of the code signing also validated. And then here's the thing about that trust boundary, that trusted zone that you can get the image copied to in the internal memory from, for example, flash memory to get it allowed to be executed. So the destination, what address the code should be copied to, and the size of the code must be within a whitelist. Now, the destination from reverse engineering the bootloader that the code is copied to is 0x8, well, a 32-bit integer starting with 0x8 and the rest zeros. And an addition that they add to that checks is that the arithmetic is also self-evaluated, so you cannot cause any overflows when parsing these images, except also that was not that secure as Qualcomm states it to be. And the above applies to headers, certificates, and other size or offset calculated items that are used in the secure boot. So at first I took a look at the actual implementation of the cryptography, because believe it or believe it not, cryptography is usually a thing that is hard to implement very correct. And when you find a flaw in the cryptography, it gets easier to get code execution at boot, because you can just sign your binary image or exploit a vulnerability in the signature checks. So at first, like I said, there are 3 certificates: the root certificate authority that verifies the attestation certificate authority, and optionally there's an attestation certificate that's unique for each firmware, but it's optional, though in all devices this attestation certificate is usually embedded because code signing is enforced. So on production devices you'll pretty much always find an attestation certificate. Certificates are signed by the next certificate in the chain, and the verifications is done by calculating a SHA-256 hash digits of the root certificate authority at first, and that was the value that's stored in the ROM. kind of like with the Nintendo Switch, sorry, the Nintendo 3DS, the boot 9 strap. It also compares a hash value from SHA with the value in the ROM. Server-side signer cannot revoke the authorization of root certificate authorities because the root certificate authority signs attestation certificates directly and is entered to the ROM on device. That means that if a certificate gets compromised, there is pretty much nothing that Qualcomm can do, and there will always be, well, the possibility of signing your own code. The root certificate authority and the attestation certificate authority are similar to SSL certificates, and this attestation certificate is an important one and very different in comparison to the other certificates because it contains some core specific information for Qualcomm encoded in organization unit fields. So these fields, I'll just quickly walk through them because they're important. They serve also as an additional mitigation against downgrading to vulnerable firmware. So let's say you are able to sign any code. Then there's also this thing that the software ID of the image is compared to the previous version that is installed. And if this version is that is installed is higher than the version that you want to restore, then it prevents it from downgrading to that version. Then there is also that each firmware is unique per hardware device, and a hardware identifier basically consists of a family, unique chip ID basically, and a model ID. So that makes the signing process pretty unique to each device, so that you cannot sign for a bunch of devices just for one device specific. But like I said, the attestation certificate is validated by the other certificates in the chain, so Qualcomm can pretty much sign for any device. Now, there is also a debug field, but of course, when you patch it for adding more debugging to the bootloader, that won't work because it will break the code signing chain. And the standard value is 2, which is disabled. I'll just walk through it. Oh yeah, and then there's this field, software size. And at first I thought, okay, can I just change this size to bypass the signatures? But, well, they state in their secure boot documents that it's not used for validation, just for information only. But this one, the algorithm that's used is also for the verification of signatures is also stored in the organizational unit field of the certificate. And that's a weakness because SHA-1 is a way weaker signature verification method than SHA-256. So it's considered a weakness. Of course, most certificates nowadays come with SHA-256, but since you can patch this, yes, that will break the signature chain. But if you patch this to SHA-1, it will use SHA-1 to validate and basically relax the signature verification a little bit. Because even when the signature is broken, it still tries to verify this with SHA-1. And when it compares this to the 256 SHA hash in the boot ROM, it will only compare it to the size of a SHA-1 hash. Now, the Qualcomm operating system, coming back to that again, AMSS, is very useful, was very useful in reverse engineering how Qualcomm works when everything is bootloaded and started. It also contains a lot of asserts to absolute paths with also the name of source code files. I've tried looking up on the internet but couldn't find them as everything is proprietary. I pretty much hoped them to be leaked, but they were not. But eventually I started working on my own ELF parser to analyze these files and parse them more easily. And coming back to the OKL4 kernel that's used in this operating system, this code was once open source, and you can still retrieve it through the web archive. So if you go to web.archive.org and you go to the OKL4 kernel website, OKL4 labs, Open Kernel Labs, that was it. Open Kernel Labs. Then you will see that that you can still get the source code. I'll release the source code on my GitHub repository. I've already released it there because they removed it from the site, and the reason for that is that, well, Open Kernel Labs pretty much is deprecated since 2013, and everything that was once open source is now proprietary and private. And they also removed the code. Their entire website is down. But through the archive, you can still get the source code. So I compared that source code to the IDA image, and it was almost the same. Almost any function that was originally from OKL4 was still used in the iPhone 5's AMSS image. Now, the OS bootloader is the operating system bootloader, generally loaded each time that the baseband is being booted up. It's on iOS in a folder /user/firmware/baseband. You can find it there. And it's loaded each time, but of course it's also code signed. And then I figured out what the header was, as you can see here in the picture. So it also says this image destination pointer. That's a pretty important one because that will tell what address it should load the code in of the trusted memory. So you can control that when creating a firmware image. And basically, if you just make it 0x8000 or within the boundaries, then it will valid for that. It will be valid for that part. But of course, the code signing is not valid then. The device bootloader implements deload, which is a protocol used by Qualcomm for emergency debugging and flashing. There are two types of implementations of this protocol, and streaming deload and deload. But this is amazing because each time the baseband crashes, so you just need to find a way to crash your baseband, the device will enter streaming deload. And this deload accepts commands via high-speed USB that can be fast if you know the command types. Luckily, I found open source libraries that pretty much already implemented the structures of these commands that you can send to it through raw USB packets, high-speed USB packets. And this deload mode is on the NOR of the baseband. So yeah, you can pretty much not break it. It's to prevent the baseband from breaking. So here's some details that I was able to forensically recover from the iPhone 5 through strings utility on Linux, through binlog, through Radar2 and IDA. Yeah, so there are some internal names that I got for the specific baseband version of the iPhone 5. Also, you can retrieve the data sender that the baseband was signed with by looking at the certificate. You can see version numbers on the programmable ROM and the NAND, which is pretty cool because the NAND is from MicronTech, which is what the MT stands for. Then the 29F means the 29 family of MicronTech NAND chips, 4 gigabytes of NAND storage, 16K of pages, and this is some revisions. Now, the iPhone 5 is a little different to its predecessors because it uses the Qualcomm Hexagon DSP6 processor. And what makes the Hexagon DSP6 processor different from normal ARM processors is that the Hexagon processor implements some special memory protections that verify the context for which pointers are referenced. This is to, that's from what I understand, this is to prevent attackers from executing from contexts where they shouldn't be executing. which makes it harder to exploit this architecture. But the Hexagon SDK is publicly available, and the special instructions you can even use with the Hexagon SDK. Of course, not all private instructions are in this SDK, but yeah, a lot of useful instructions will be in the SDK. You can compile source code for the Hexagon, which you will use when exploiting bugs in the Hexagon architecture. Then this was like a gold mine to me. I found that a special debugging mode via streaming deload allows you to dump certain memory regions via USB, via serial command line. So you can dump the USB high-speed USB interface buffers. You can dump the UART buffers, the NOR. You can even dump boot ROM and well, some other core memory files, which is pretty useful. And I can show you how it looks like in IDA. I wasn't able to use the Hexrace decompiler for this, but luckily I was able to decode it with Snowman. As you can see, this is the code, and this is where it dumps it, and then here you can see what it can dump. This is basically, well, this is where the offset, so the SDRAM is at offset 0x8000000, etc., etc., and this is the files it will dump it to, and the dumps will go into environment RAM. So yeah, that was pretty cool to discover, and useful for future debugging when trying to analyze the firmware to find bugs. In Sahara mode, which is the recovery mode in which you can restore normal images, like updating the OS bootloader, etc., etc. This is also the mode in which each time the images are loaded when the baseband is booted up. So you can, at first, file system is loaded, then the internal apps bootloader is loaded, and then the firmware and software images are loaded for the processor. The boot authorization is done, and a checksum is done to verify that the boot succeeded completely and everything went fine. The run section for executable code is created. And also what I found here in this architecture is that there is no modern exploit mitigation, so that also means that there is executable stack. So pretty much, yeah, execute anywhere. Qualcomm also has a power management module, which they refer to as RPM, but it's pretty complicated, so I haven't looked into it. So what made analyzing this firmware easier? I used tools such as Binwalk and Radar 2, but that wasn't that easy at the beginning. What it made it really easier to analyze this firmware is that the firmware was not encrypted. Binwalk screwed up with the extraction. It produced some rubbish, some zlib files, but it was maybe not that efficient at first, but it was still informative, as it disclosed me that the images were ELF images, and it also disclosed me that the images were not encrypted, and it also told me that there were 3 certificates and at what locations they were, and I could extract the certificates, which were the attestation certificate, etc., etc. Radar 2 was not quite useful because, in this case, because basically I didn't know that there was an additional header for the, well, basically the Qualcomm images above the ELF header. So yeah, that pretty much made me disassemble at the wrong offset. So yeah, after that I got Radar 2 to work, and I could disassemble the entire file from the right offset. But my solution to this, before I knew that there was this special ELF, the special header above the ELF header, I started working on my own ELF parser, and it worked fine. I just did an fseek and C to search for the ELF header magic, and then I started parsing the ELF image from there. So eventually, I also created a structure for the mobile baseband file format. And eventually, I might work on an offset finder so that you can find common functions used in the bootloader and the operating system for later patching. Because that brings me to the following known vulnerabilities in baseband firmware. It's not actual vulnerabilities. These two, executable stack and no address space layout randomization, but it makes it pretty easy when vulnerabilities are found for an attacker to override functions in the firmware, like specific checks, such as the the signature checks, and this I still see it as some kind of vulnerability because address space layout randomization should be implemented in such devices. They were not that old. The iPhone 5 is not that old. Many devices already had ASLR back in the days. But also, it's not uncommon for baseband chips not to use ASLR due to performance. Then there is a buffer overflow that I found in public CVEs that I tried to use, but then I figured it was just a buffer overflow that lets you overflow into a kernel debugger buffer, and you cannot control in any way through this. So that was not sufficient. And in the ancient times of the iPhone 4, there was a xlog AT command stack-based overflow that was exploited for baseband unlocking, but sadly it's been patched. So that brings me to the following cool thing that I again found is that on a forum I found Qualcomm XDM, which is an extensible debugger for the Qualcomm baseband. And it was pretty complicated because this baseband tool needed a license, but the license was provided on the forum, so I thought, okay, just for research purposes, I might try it out. And sadly, this license was expired, but as you can see, I managed to patch the software, and there was just one single jump not zero instruction that I could patch to jump zero. Basically, it's Intel, so it's not that hard. In IDA, you can use IDA patcher for that. And that jump not zero jump to a function returning the remaining days. So I pretty much patched that. And could in theory use this tool, but I have not been able to use this tool yet because I do not have a serial USB device for working with the Qualcomm high-speed USB protocols. Then I decided that fuzzing probably was the best way to trigger some bugs in the baseband. So I started researching how can I access logs for when a baseband crashes. And I know that logs are saved in iOS and can be synced to a PC via the Apple File Conduit protocol. But logs did not contain any registers, only mentioned the error code and when the crash occurred. So I pretty much found how to enable extensive logging by reverse engineering communication center daemon in iOS that talks to the baseband. And based on that, I still got some more output, but still no registers as baseband crashes are stored in the baseband environment RAM. And the access to this environment RAM is known to be prohibited. I wasn't able to access it, but there are probably some undocumented commands to get access to the environment RAM. So building the fuzzer is quite a challenge, and I'm still working on one because it takes a lot of effort to effectively fuzz all protocols, and these protocols can be very complicated. But these are protocols used by Qualcomm that you can use for fuzzing. The QMI protocol is pretty extended, and it's a new and complicated protocol, but also new and complicated means that, there might be bugs there. So this is probably the most profitable protocol when you want to fuzz baseband from Qualcomm. You can also fuzz through Sahara, the restore mode in which you can upload restore images, or the SD load and deload interfaces for emergency restores. But there is one protocol for diagnostics that also has a lot of commands. And in the past, there was this peek and pop command for, well, letting you take a look at certain memory locations of the baseband. And this was exploited to, again, unlock a baseband, a carry-along baseband. But it's patched now. So also diag is a good interface for fuzzing. Fuzzing through AT commands is also a good way, but it's a bit harder because Apple removed all serial interfaces to the baseband. So there's only a way to fuzz AT commands through their communication center, and you would need a jailbreak for that to access that communication center and inject code into it for fuzzing the commands. And yeah, well, there's another attack that you can do on lower level when you are in SD load and deload mode, and that's by just trying out random firmware images. So building the fuzzer can be done on top of libqmi, which is an open source library for the QMI protocol from Qualcomm. libopenpst, which is pretty much used for all other protocols in the QMI interface. The AT commands are, of course, many of them are proprietary, but there is some documents online leaked or even documented by other researchers. And well, I've put a link up here to some AT commands that you might try out for fuzzing. But well, the GSM stack itself of basebands is also a vulnerable aspect, and this is the only aspect on which you can remotely compromise baseband devices. So for fuzzing via radio, you would need to hacker F1 and GNU Radio installed on Linux, and then you can pretty much send type 0 SMS and other specific parts of the GSM stack that you can target and send to via radio. So yeah, in the past you could send AT commands over serial interfaces, like I said, but they're disabled nowadays on the iPhone 5 and higher. But now comes the cool stuff. There have been vulnerabilities in the secure boot of Qualcomm, and honestly, it was like a big flaw in Qualcomm. They cannot patch this because yeah, you can pretty much restore to any bootloader now, because you can just let the bootloader always be valid. So as you can see, this is the secure boot file in which it compares the signature length, but yeah, it compares using the signature length from the image header instead of the certificate chain. So in theory, you can just well, pass an invalid length and make the image valid. But the next is, I also have the code for this vulnerability, but sadly, due to proprietary reasons, I will not disclose the code of this vulnerability here in this slide, but I can disclose the problem. And the problem is that when basically they forgot to implement the entire image signatures, the entire signature verification. So when you restore to this bootloader that's affected, you can restore to, well, you can pretty much, it's always valid. So when loading an ELF binary, the secure bootloader was not properly verifying ELF headers and the program headers before loading any subsequent segments from the ELF file. As a consequence, it's possible to skip verification of the segments entirely if the respective program header entry that points to the segment containing data used for cryptographic verification is missing. So basically just remove the segment of the code signatures and the bootloader will be valid because there's insufficient parsing. This is a really big flaw in Qualcomm baseband bootloader secure boot chain. And this is the only way I know so far to get code execution on boot without actually having to do a lot of stack buffer overflow exploitation. So yeah, this is the best case of exploiting the baseband. And since you can exploit this by just taking the assigned bootloader of this version not even a signed bootloader, you can restore always using this bug. I believe the iPhone 4S and the iPhone 5 are both affected by this bug, and the iPhone 4 as well. So future developments, I'm creating tools useful for researching baseband, accessing the interfaces of the baseband, and I also want to create a tool for loading custom firmware images through the protocols of Qualcomm, so you can restore custom bootloaders and that kind of things for future developments, creating custom firmware. And I, of course, will take a look at this image signature verification being missing in a specific version of the bootloader. I'll try to find the specific bootloader version so that you can use it to restore the custom firmware. So these are some references. I'll put the slides online after this presentation that you can use if you want to access these interfaces. POSIX Ninja has helped me a lot during this research, so big shout out to him. Go follow him on Twitter. It's POSIX Ninja, just like here on GitHub. And then there is also some resources that I used. Osmocom is a very cool group researching Qualcomm baseband. They have created custom firmware for some open source, some consumer-based Qualcomm baseband chips. But yeah, for the iPhone 5 and everything, baseband is proprietary. But a lot of information came from Osmocom for this presentation. Also, Qualcomm has a lot of internal documentations, but it's all proprietary and confidential, so you should just sign up. Signing up is free, and anyone is allowed to sign up. You can access the information there yourself. Just do not share it with other people, because that's the policy of Qualcomm. Then there's the core telephony framework that you can look at from iOS, where the communication center is based, the daemon that communicates with the baseband. I took a look at someone who dumped the header files from that framework. There's also a tutorial here on how to inject code in communication center and debug. And these libraries, they were also very useful when creating tools for examining the baseband. Then at the very last, I want to give a big thanks to the developer of this utility. This utility that provides a full command line for accessing the protocols of Qualcomm. So if you have a device that opens itself for universal serial bus communication via high-speed USB, then you can use this tool to get a command shell and interact with all the protocols from Qualcomm. So that's the presentation for now. Are there any questions?